Okay. So in the last class, we have completed till here, right? So the general trend that we discuss is along the period or across the period, when from right to left, what we have observed that the ionization energy increases, and it is increases. There are three factors: because the nuclear charge is being increased, the number of protons are being increased, electrons are being added in the same shell, so the shielding effect remains same, and the attraction gets stronger, and the size decreases a little. So as a result, it increases, the ionization energy increases. Okay. Assalamu alaikum, Mariam. How are you?
Walaikum
1 minute. I'm not able to hear you. Okay. Yes. Am I audible to you?
Yes, sir, you are.
Okay, but you are not audible. Okay. So now we
Sir,
are,
could you hear me?
yes, now I can hear you. Thank you. Okay. So the next thing that we will be discussing, we are actually going to observe the ionization energy value from one element to other element very specifically in the period.
सर आपकी आवाज बहुत ज्यादा कम आ रही है
1 minute. What about now?
Yes, it's better.
Okay, great. So if you guys open a periodic table, so let's take the example of period 2 and period 3. That's what we have mentioned above. That in period 2, the first element is lithium. Then the next one is beryllium. Then the next one we have boron, then carbon, nitrogen, oxygen, fluorine, and neon, right? Then in period 3, yes, it starts from sodium. Yes. So we have sodium, then we have magnesium, then we have aluminium, then we have silicon, then we have phosphorus, then we have sulfur, then we have chlorine, and then we have argon. Okay. So what I'm going to do now, if you guys have ionization energy data, so you can easily able to relate we are done with the general discussion along the period that generally the ionization energy increases across the period, right? Now we are going to observe specifically and very closely from one element to another element in the periodic table. So on y-axis, what I'm going to put, I'm going to put ionization energy. That is in kilojoule per mole. And on x-axis, I'm going to put elements. Okay, tell me, if I compare lithium and sodium, which one have a greater ionization energy? Sodium. Sodium. Yes, Mariam.
Yes, sodium.
You all of them forgot that down the group ionization energy decreases. The forces of attraction gets weaker because the number of shell increases, distance increases, shielding increases, which outweighs the nuclear.
Sir, did you ask ionization increases or decreases?
Ionization energy decreases down the group, and across the period it increases. So I just asked you about lithium and sodium. What did you say? Did you, isn't it you said that it increases?
Yeah, I said ionization increases
Yeah,
in
and
sodium, which is wrong.
yeah, so sodium, isn't it the sodium has the lower ionization energy because of its a greater size? The electron is far,
Yes.
the nucleus, there are more shielding as compared to lithium. So down the group, the ionization energy decreases, but across the, down the group, the ionization energy increases, and down the group, across the period, ionization energy increases. Okay. So if you look over here in the data section, okay. So a moment, what you need to do, and anyone else who don't have, just search on the net whenever you get the time for the chemistry 9701 syllabus, and you guys will get this document. Yeah, but it is, you can find it in the document, in the PDF document from page 80. From page 80 till page 91, till the periodic table. So you must have this in the hard copy. Can you show me yours? But it is very old. There are different things now. There are lesser things. But we have a data section thing. They, instead of this whole data, yeah, yes, and they give you the information with the question instead of the data. आप अभी बताते हैं क्लास के बाद, मैं भी बोल दूंगा. Okay, so if we go over the first ionization energies of period 2 elements, let's say. So in the period 2 element, the first element is lithium. If you see, what is its ionization energy? 519. Okay, let's assume that this is over here. I'm just plotting it over here. Then the next element is beryllium. What is its ionization energy? 900. Right? So it is almost going to be, let's suppose it is over here. Okay. Then the next element, boron, which is the third element, and it's 719. So it gets lower, right? And slightly lower, only a difference of 100. So it is just slightly smaller than the beryllium. Is this clear? Then the next one is carbon. If you see, it's 1090. So if it's 1090, so it means it is greater than beryllium as well, right? So I'm going to plot it a little high like this. Yeah, that's what I'm going to discuss. Yeah. And then the next element is, after carbon, we have a nitrogen. And then nitrogen is 1400. So I am going to plot it over here like this. Okay. Then the next one is oxygen. And for oxygen, it goes 1310. So again, slightly down, right? And then we have fluorine, which is 1680. It means even greater than the, not just nitrogen, but greater than oxygen as well. And then the next one is neon, whose is 2080. So we will be getting a graph like this. So examiner also give you this graph to draw, and it's for 3 marks because you have to keep these inclines and depths both in your mind. That when you are going to making the lower ionization energy, you must keep in mind that it must not be equal or lower than the earlier one. Yeah, it is just goes slightly down from the one that is just previous to it. Is this clear? Okay. So
Sir, across the period, won't the graph be like constantly increasing?
no, it won't. But the general trend, what we have discussed, that there is a general increase. So that's what we are observing. There are 2 points where there is a depth. So we are going to discuss that reason, and that reason examiner also asks us in the paper. But in general, if you see the first one and the last one, so what is the general trend that it increases? So if examiner just ask you to show or explain the general trend across the period without mentioning anything, then you are always going to explain these points that we done in the last class. Is this clear, Mariam? Nile?
Yes.
Okay. So over here, the one which I have plotted is starting from the period second, first element, that is lithium. Then we have a beryllium, then we have a boron, then carbon, then nitrogen, then oxygen, then fluorine, and then argon. Now, if we move to period 3, we again going to observe a same trend. Let's start with period 3. The first element is sodium. Its ionization energy is 494. So you can see it is lower than the lithium. That's what we have discussed, because down the group, the ionization energy decreases. So every element of period 3 has a lower ionization energy than the period 2 element of the same group. Is this clear? Okay. So sodium has 494, right? Let me plot it over here. Then we have a magnesium, which is 736. Then we have aluminium. It decreases than magnesium, but not gets lower than or equal to sodium. It is still higher than sodium, right? Then we have silicon, which is 786. So it is even more than magnesium, right? Then we have silicon. Oh, yeah, it's silicon. So we have a phosphorus, which is 1060, even increasing. Then we have a sulfur, which is 1000, a slightly lower, right? And then we have a chlorine, which is 1260. And then we have a, okay, sorry, it's neon on the top. So argon, which is 1520. So again, we are getting the same trend over here. So in both the cases, what we have to have, what we are observing, that the general trend is increase. The last one has the lowest and the, so sorry, the first one has the lowest and the last one has the highest, right? So it is, we have sodium, magnesium, aluminium, then we have silicon, then we have phosphorus, then we have a sulfur, then we have a chlorine, then we have a neon over here, and over here we have a argon. Is this clear? Any confusion so far? Okay. Now, Mariam.
No, sir.
Okay, but the thing is that in both the periods, what we are observing, that exactly the same trend. The positions where there is a dip in the period 2 between the two elements, we are observing the same dip in period 3 as well, right? Like when the element is from, when we are moving from group 2 to group 3, beryllium is in group 2 and boron is in group 3. Similarly, in period 3, magnesium is in group 2 and aluminum is in group 3. So there is a decrease in ionization energy. And then the same way, when we move from group 3 to group, oh sorry, group 5 to group 6, from nitrogen to oxygen or phosphorus to sulfur, there is again decrease in the ionization energy. So these are, for this, you need to remember the reasons, and that's what I'm discussing. Okay, you are not aware with the electronic configuration for the A levels, right? So I just tried to give you a little hint about it right now, so you can able to understand. So first we are going to discuss the reason between beryllium and boron. Okay. Yes, do it with the pencil. Okay. So ionization energy of beryllium and boron. So beryllium has 4 electrons in its valence shell, and boron has 5 electrons. Sorry, beryllium has in total 4 electrons, and boron has 5 electrons. What is okay? So we will do it later. Yeah, aluminium. Yeah, magnesium and aluminium. There is a decrease, and there is a decrease. Okay. So what we know that there are 4 electrons. So the 2 electrons are should be filled in the first shell, and the second shell also have a 2 electrons, right? So, but the thing is that now we write the electronic configuration like this: 1s2 and 2s2. The paration. Yeah, that S is further division of a cell. First shell has only one division, and we call those divisions subshells. So the first shell has only one subshell, that is S, and that S has 2 electrons. And in the second shell, again the first subshell is S, and that has 2 electrons. Okay. Now for no, it is going to be 2s2 and 2p1. So that is the difference. Now, if you see the electronic configuration, then you get the hint what is happening over here. Why there is a dip in the ionization energy. The valence, yeah, the valence electron of beryllium is in 2s, and the valence electron of boron is in 2p. 2p is further away from the nucleus. There will be more shielding because now there are 2 subshells between the valence shell and the nucleus, right? So the force of attraction gets weaker for in case of boron, and the ionization energy decreases. So that is the reason. Is this understandable? Yes, Mariam, did you understand this?
Yes.
Okay. So that is the reason that you are going to write. And it means for magnesium and aluminum, the reason is going to be same. The only difference is that,
Sir, will we get a recording of this class?
yeah, I'm recording. Yep, the class is being recorded. I'll share the link. Once I upload the recordings, I will share the link. Okay, till here is this clear? Okay. Now, you guys need to note that down, note this reason quickly. Okay. Then, okay. So that is exactly the same thing. You guys will get the handout. So there is no need to write it twice. Yes, moment understandable. Shall I move forward? Okay. So for magnesium and aluminium, it is going to be the same thing because magnesium is exactly below the beryllium and aluminium is exactly below the boron. So only difference is that now the electron of magnesium is in 3p, 3s, and aluminium is in 3p. Okay. So the whole reason remains same, that aluminium has a valence electron in 3p. Magnesium has a valence electron in 3s. 3p is further away from the nucleus than 3s, and 3 and aluminium have a more shielding effect. So there is weaker attraction in the atom of aluminium towards the valence electron, hence the ionization energy decreases. So that is the reason is exactly going to be the same. Is this clear? Yes. Yeah, sure. First, complete this electronic configuration. For the ionization energy across the period, these are the two dips. Yeah, the between nitrogen and oxygen and between phosphorus and sulfur. That's what I will be discussing. Yes, clear moment? Nile, Amdad. Yes. Mariam.
Yes.
No, three. Actually, third shell have a 3 subshells. So yes, first one has only 1 subshell. Second shell has 2 subshells. Third shell has 3 subshells, and fourth shell has 4. That's it. Okay. So yeah, the third subshell is represented by D, and the fourth is represented by F. Yep. So now we are going to discuss the exception or the deviation in the trend between nitrogen and oxygen. Oxygen gets lower than the nitrogen. So again, if you write the reason, before that, write the electronic configuration. So if I write their electronic configuration, 1s2, 2s2, 2p3. Now, different subshells have a different space for electrons. Okay, so what you do for a time, and 1 minute. Just take the picture of this, so you will get the idea. Just take the picture. Take it from here. It is more clear. Take it from here. Okay, first read the thing which is written extreme on the left. Okay. Okay. Now, oxygen has 8 electrons. So 1s2, 2s2, and 2p4. So, Moment, did you see that the shells have subshells, and those subshells have further orbitals, and that orbitals carry electron? Now, if yeah, 6 electrons are there, but how many orbitals are there in the p subshell? 3. Yep, very good. 3. So it means that over here in nitrogen, the 2p, the valence subshell has 3 orbitals. And over here, again, the valence subshell has 3 orbitals. Okay, now when I'm going to fill the electrons in these orbitals, I represent it like this. As in nitrogen, there are 3 electrons only. So first, each orbital get 1 electron. So all of the 3 orbitals of nitrogen has 1 unpaired electron in each of them. But when it comes for oxygen, oxygen has 4 electrons in the p subshell. So when I fill those electrons in the orbitals of p, so first each one get 1 electron, and then one of the orbital get a pair. Okay.
Sir, so oxygen has a higher ionization energy?
No, oxygen has a lower ionization energy, isn't it? That's what we have discussed in the data. From the data, that's what we have plotted. Now I'm going to explain you why. Now tell me, we have discussed the spin pair spin. So did you recall, Mariam, when we discussed this, that the electrons are being paired up? So why did they get paired up although they are negatively charged? Isn't it both the electrons are negatively charged? So isn't it then they meant to
Yes.
repel each other, but still they are getting paired? So what is the reason? Can anyone recall? We have discussed.
Because
Yes,
because they're spinning against each other.
their spin
They're
is
not spinning in
their
the
spin
same
is opposite to
direction.
each other. And what if their spin is changed? Then what happens to their repulsion?
Could you come again? If they're
What happens to their repulsion, or how their repulsion is being affected due to the opposite spin?
they don't get repelled that easily because
Yeah,
opposite
or
direction does
actually
not
we can
matter.
say that their repulsion gets minimized. It doesn't mean that they have no repulsion. Yeah, they do have a repulsion, but their repulsion is minimized. But they get further away from the other one. See, 1 minute. That's what we have discussed in the class, I think, on the last Thursday. You were not there, moment. So that's what we have discussed. When the electrons pair with each other, those which have a opposite spin, and for the opposite spin, we represent them like this. If both are in the same direction, then they have a same spin. Right? So what we have discussed, that the repulsion between electrons is the electrons which get paired, they minimize. Does it mean that there is no repulsion? It means there must be some repulsion between that pair. Did you get this, Mariam?
Yes.
So it means now if you compare this electron, is this electron feeling any repulsion?
No.
Because it is unpaired, right? Is this electron feeling any repulsion? But what about this pair? It is feeling the repulsion. There is some repulsion. And over here, there is no electron which is feeling the repulsion, right? So if this pair, due to the pairing, they are experiencing a repulsion, they are repelling each other. So it means that one of the electron gets a little further away from the nucleus, right? And that's why the now this electron is going to be gets removed from the nucleus easier than these one, because this is far from the nucleus. And if you see this, this is only a repulsion which is creating a very slight difference. That's why if you observe over here, that you will find that this depth, this dip is relatively very small. See, it's 1400 and it's just 1310. Only the difference of only 90 unit. It's just slightly decreasing. It's not that it is decreasing very with a greater value. Is this clear? Yes. Yes. Did you get this, Mariam?
Yes.
Okay. So examiner asked this reason as well. These reasons are usually for 2 marks or 3 marks. So we are going to write about this, and we call this repulsion spin pair repulsion. So in oxygen, there is a one of the valence orbital has a pair of electron, And in phosphorus, one of the 2p orbital, none of the 2p orbital has paired. So that pair of electron repel each other or experiencing a spin pair repulsion, that makes the electron a little further away from the nucleus, hence the ionization energy decreases. Is this clear?
Yes.
Yes, Mariam, did you understand this?
Yes, I did.
Okay, great. इस रीजन को जल्दी से कॉपी कर लें और then for phosphorus and sulfur it is going to be exactly the same because they are just, phosphorus is just below nitrogen and sulfur is just below oxygen.
अच्छा तो दोनों पे जो सेम एक्सेप्शन है
Hmm.
सेम ग्रुप में जो एक्सेप्शन है वो सेम रीजन है
Yep. Between the same groups, the exception is due to same reason.
जैसे सेम नहीं होता है
At 2 points, it is slightly decreasing. Yeah, these are the exceptions or deviations from the general trend.
सर तो सर में
Hmm. Yeah, these, you are talking about these? These are decreasing. So this is the X deviation. Sorry. There is a general increase, right? See, if you see lithium to beryllium, it is increasing, boron to carbon to nitrogen, and oxygen to fluorine to argon. So this increases due to this reason where we have ended the last class. There is a general increase, right? But there are 2 points in the period where there is a dip, and we have discussed their reasons. Clear? Yes, Mariam, are you done with the reason? Imdad?
Yes.
Imdad? Can you just wait for 2 minutes? Thank you. Okay. So the next thing that I'm going to discuss is about successive ionization energies. Successive ionization energy means after removing the first electron, we will remove the second one, then third one, then fourth one, and so on. Just leave it, leave the space, do it later. Okay. So if successive ionization energies are given, then these are helpful in identifying the number of valence electrons and group of the element in periodic table. Okay. So how we will able to figure out the group? Let's have a look at example. Let me take the example of phosphorus. How many electrons it has? 15. So if I write its electronic configuration, it is going to be like 1s2, 2s2, 2p6, 3s2, and 3p3, right? Okay. So, Mariam, when I remove the first electron, that is the first ionization energy, right? So,
Yes.
which electron, the electron that is removed at first point, from which subshell it is?
3p.
3p. So what we are going to do? We are going to remove the electron from, when we provide the energy, the first electron is actually going to be removed from 3p. Is this understandable to all of you?
Yes.
Okay. Now think, if the electron that is removed from 3p, it needed this much energy. It needed this much energy, for example. So as a result, what happens that this phosphorus atom now turned into +1 ion because one electron is lost. Now, if I provide further energy to this phosphorus, it can lose the second electron. But obviously, for that, isn't it, I need a more energy because now I'm providing the energy to a species which is already a positive charge. So it means it is holding the rest of the electrons with the more attraction as compared to this one, right? So it means more energy is needed. So there is a little increase in the energy when the second electron from the 3p is removed. When I remove, if I provide the further energy, then what happens? The next electron is removed, but it needs even more energy, right? Because now the electron is being removed from 2 positive charge cation. So that would be like this. Is this clear?
Yes.
Yes, Mariam? Is this clear to you as well?
Yes.
Okay. But now after these three, the charge is increased further. And now the next electron is going to be removed from the inner subshell,
Yes.
right? Total 8, but that has 3 regions.
So that's how it's split.
Right now you can understand like this. Yeah. Okay. So now the next electron is going to be removed from 3s. So it means now that it is further closer. It is more closer
More.
and more charged. So more energy, but now the gap, the difference is slightly bigger than when the electrons are being removed from the same subshell. Is this clear?
Yes.
Then the next electron is removed from 3s. So a little higher energy because the electron is being removed from same subshell. Is this clear? Yes, Mariam?
Ji, sir.
Clear till here?
Yes.
No. No. Because there is a very high charge. The 2p, when you reaches there, what will be the charge of phosphorus? It lost how many electrons? 5. So it is a +5. So that repulsion is actually become very insignificant due to the highly positive charge. Yeah, but because the high positive charge makes the attraction very stronger, so we need a higher energy. Okay, now the thing is that after this, the next electron is being removed from 2p, right? So the thing is that now what happens? Not just the subshell is changing, actually a shell is changed. Initially, the electrons are removed from third shell. The first 5 electrons which I have plotted over here, they all remove from third shell. Now the next electron is going to be removed from second shell. So we are going to observe a big jump in the energy because now the electron is actually removing from inner shell. And now how many electrons are going to be removed from this subshell? 6. So there is a gradual increase between these 6 electrons like this. And then again the subshell changes. So a slightly bigger. And then again, now again the shell changes, right? So again a bigger. Is this clear? Yes, Mariam, did you understand?
Yes.
Yes, Momin, is this clear to you as well? Okay. So I'm going to plot it like this. Now you guys have a very small task related to this. I made this graph. Examiner also give this kind of a graph as well for 2 marks to draw. Now what you guys need to do, you guys need to draw the same graph for carbon, aluminum, magnesium, and sodium. Now you can go to the restaurant. What time? No. Just you need to show that this trend which indicates where the subshell is changing, where there is a shell is changing.
Sir, is the class over?
No, you need to draw these and WhatsApp me. Yep.
I thought this was the home task.
No, this is not the home task. Do I need to discuss one more thing? Yeah, but you can want to leave. You just send me the afterwards on WhatsApp your task. Okay.
Yeah, that's fine. I'll do that.
Okay, great. Keep that distance even bigger. So if you want to leave, Mariam, you can leave.
Okay, thank you, sir.
You're welcome. Yep. Yes. No, I will check. Problem. The gradual changes. No, count the electrons. You put the 11 electrons. Why the middle one goes up and then the other one comes down? Yes. 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 How many electrons S is getting? Every time S is getting 2 electrons, so 3s2 and then 3p1. Okay, you do one more thing. Yeah, S always get the 2 electrons. You got the picture, right? And yep. And this is the rule for writing the electron configuration. We will follow these lines. You can take the picture of this one. Two electrons, six electrons, two electrons, six electrons, two electrons, 10 electrons, six electrons, two electrons. Okay. That